Hello and welcome to the Tech Forum. It's had its summer holidays. It's back in fine form for the new term at school. So we've got a good lineup today. We've got Lee kind of speaking about Unikernels, kind of latest, greatest tech that's coming up. So over to you, Lee. Thank you very much.
Thank you.
Hello everyone. So we're talking about Unikernels, which if you have no idea what they're talking about, I'll give you a slight hint that it's kind of on the edges of virtualization, operating systems, and some relation to containers as well. It's just an introduction to the topic. I'll do a little demo towards the end of a practical use of it using our own code. But it's probably worth stressing that this isn't stuff you're going to go and deploy tomorrow. Maybe you could, but probably wouldn't recommend that yet. I'll also say that I'm not a systems programmer, so I'll cover some introductory stuff on operating systems and things, but I'm not a systems programmer, so this is kind of stuff I've read about rather than stuff I'm expert in. And I will try and cover a lot of the basics and build up to sort of more detail on what a unikernel is. But for some of you, if you know operating systems well, just kind of zone out for a little while, and then we'll come back to it. So, if we're talking about unikernels, we'll start off by talking what a kernel is. And the kernel is a computer program that is the core of a computer's operating system, which is fine if you know exactly what an operating system is. But operating systems are generally not defined by what they are, but what they do. So what does an operating system do? It provides access to peripherals, including I/O devices. Early computers, you would kind of, you wouldn't have peripherals, the kind of state of the machine was your I/O, but also you would have to write code to kind of read stuff off tape or put it out to some output, and it would be, you'd do that each time. Early operating systems, they started bringing abstractions that allowed you to do that, and you get to the point today where you don't really care if you're writing to a sort of Seagate Barracuda hard drive. Your operating system takes care of those abstractions, deals with the storage controllers and various other things. More generally, it provides a stable API for programs to interact with. So you have system calls like dealing with I/O, but you also have things like what threading models are available on the CPU or to enact on the CPU. What general utilities are available? Do you have the C library available, for example? And this kind of wider abstraction is standardized in some cases. So POSIX is a well-known standard for this. Most Unixes, if you squint, implement it. Windows does if you install Cygwin. And it gives the programmer confidence that they can write against known abstractions without delving into too much on how they're going to work on different machines. But the interesting bit for today's talk is that an operating system executes programs. It's the first program to be loaded at startup of a computer, and then it will go on to do other things. So it may start up a web server in the background and make it as a daemon and off he goes, but it's the operating system that manages that. It might bring up a window manager that lets the user decide what applications to run, in the case of Windows or Mac OS X or any of the ones you can get on Unix. But this hasn't always been the case. Early computers, such as Colossus, ENIAC, just executed the program that was determined by the switches and plugs and things in its hardware. There was no separation between the physical state of the hardware and the program. They were one and the same. As kind of computers got more popular and we wanted to start to write more programs rather than just breaking particular codes or calculating missile trajectories, you had this kind of switchover where we have one program, we want to put a new program in, which means people going in and rewiring the machine. Takes a long time, very error prone. So we've got an abstraction where we started separating the program from the machine itself. And around 1948, I think Manchester's small-scale experimental machine, known as Baby, was one of the first to do this. You could put the program onto tape and load it into the machine. When I say, in some of these history bits, I'll talk about the first to do things. It's often quite hard to know, partly because the UK classified everything until relatively recently, and also the first depends on a lot of context. So while the Baby was one of the first to do this, it wasn't the first to do it in a real-life production system. But I'll try and cover bits of that as well. But yeah, you've got the program in a stack of cards or punch tape. You can load it into your machine. much faster. You can run more programs back to back. But it's still not quite back to back. And what would happen is that as the program time decreased, because you've got faster computers, the amount of time that a computer was sat idle, because you had programmers trying to fumble a stack of cards into the reader, would increase. And you've got these very expensive machines sat around idle while programmers literally stand in queues outside trying to put their things in. So one of the early developments in operating systems was known as the GMNAA monitor. And what they did was basically wrote a little wrapper program that would allow multiple programs to be put into punch cards at the same time. And as soon as one stopped, it would pull the next one in. So you get rid of that gap between running programs. You make your utilization of your expensive computer much higher. Now, as with all systems, once you find one bottleneck and close it, you move on to the next one. And the next one they came across was that access to peripherals was slow, particularly tape. So if you had your program chugging along, it needed to get something from tape or write something to tape, there's a big gap while it goes and fetches it. So we got a thing called multi-programming, I think characterized first by the Leo 3 in 1961, where it would load in several programs into memory at once. And when one program stopped to go and take a lengthy operation, like read from tape, while that was completing, the operating system would load the next program in and start executing it, so the CPU was never left idle. This kind of evolved into what you'd recognise nowadays as multitasking. Probably Multics in 1964 was the first one to do this. And you're getting to the point where it's kind of what you see nowadays. Programs load in multiple, OSs load in multiple programs and swap between them, give them like a fair allocation of the resources to run. But that doesn't come for free. Early operating systems didn't worry about the isolation too much, but modern operating systems have to. You have to stop the programs interfering with each other when they're running what appears to be in parallel. So first of all, you need to restrict access to peripherals. So we use the operating system to govern this access. You don't want one program trying to write to a disk drive while another one's controlling the disk head. You don't want one program writing to the printer in the middle of you printing your document, because it will just end up in a mess. So you need to put in these abstractions, which basically bundle up the units of work to these peripherals into small transactions, and then make sure you guarantee the isolation, so only one process can do it at a time. So then you need to add in locks and queues and things like that, which will take time. If you've got control of the program, though, you can bypass these, because you can say, well, I won't go through the OS. I will just call the CPU and write to memory. Whatever memory I want. I won't use the OS to tell me what's going on. So you get to the point where the OS has to manage the memory then, to make sure that you can't do that, because most I/O drivers basically work by moving bits in and out of memory. It kind of says, I've loaded some data off a disk for you, and it's at this memory location. So the operating system then has to govern all the memory and make sure that you're not accessing bits out of where you should be. But to do that, you then also have to govern access to the CPU, because you could just call a CPU instruction and say, well, I don't care that the operating system is managing the memory. I'm going to bypass that and read it from there. So you kind of reach a point where the operating system has to control everything rigidly, which has an overhead. And to actually do that effectively at all, you also need hardware support. So all modern CPUs support different levels of isolation, often called rings, within them. And at a basic level, you would have what's known as like the root ring or ring 0, which when the operating system boots up, it kind of says to the CPU, I'm the master process, give me full access. Then what it will do is it will allow programs that are running to access the other isolation levels, which have a reduced instruction set. So other programs can't load things into memory unless it goes through the OS. So if you want memory, you can't go to the CPU, you don't have access to that instruction. You have to go to the OS and say, I want some memory. The OS will context switch and say, right, I'm the master process CPU, give me some memory. This creates an overhead because that switching, called context switching, between permissions in the CPU takes time. It's something that's been heavily optimized over the years, but it's still something, if you've got LM-Bench or something like that on your machine, you can actually watch happening. It does have a measurable impact. It also means that CPUs are very good at caching the work they're on, so they don't have to go to main memory for data. They can keep it in a local cache, which massively speeds it up. But if you context switch, it has to throw that state away to load in the work that you want the kernel to do, the operating system to do, and then put it back out, which slows down the program quite a lot. So we've got a nice system here, which allows us to utilize the CPU very efficiently, but we're paying a bit of a CPU price for it, and also a memory price as well, because if you're loading multiple things into memory, you have to manage your memory a bit more closely. You probably want paging. You might want paging anyway, but you're more likely to want paging if you're having to run lots of things at the same time, because the total memory you want to use might exceed the system. So it comes at a cost. So if we look at another angle to getting better utilization, virtualization, even if you can use your computer very efficiently by using an operating system to run lots of programs so it's fully utilized, in real world that comes with quite a few drawbacks. Your programs often require different configuration, so you need to be very careful about how you manage the resources of your computer, particularly disk space and things, to where you put configuration and data files. They also require dependencies, whether it be libraries, OS versions, or even OSs. So if anyone here has tried to upgrade a server that was running a web server, application server, and DB server at the same time, will have gone through this pain, that it's a very hard upgrade because they'll all kind of want slightly different things and they won't necessarily all support the same things. Good packaging kind of helps, but you've got this kind of coupling between all these things on your computer because they're all running within the same operating system space. So virtualization is a way of us kind of creating an abstraction that allows us to run operating systems in a more isolated way. So things like configuration and dependencies can be isolated as well as the programs themselves. So roughly speaking, there are two types of virtualization. We have something that we would call full virtualization, in which instead of the operating system governing access to the peripherals, CPU and memory, you have a hypervisor. And the hypervisor is just a computer program that provides a simulation of hardware. You should all be familiar with these, even if you're not using them today to day, you probably are. There's things like VirtualBox, QEMU, VMware Workstation. Well, I think that was one of the first to popularize this. Does anyone know when the first hypervisor was out? Which was the first? No. I'm not surprised. IBM CP40 in 1967. So although we think of virtualization as kind of something reasonably recent, it's like most things in computer science. It's been there for quite a long time. Another example of hypervisor is Zen, and that is an interesting one because that forms the basis of EC2. EC2 uses a modified Zen hypervisor to basically give you EC2 instances. And what is basically happening is the hypervisor provides the abstraction across those. So instead of running multiple programs, you're running guest operating systems and getting that isolation, and the hypervisor is taking care of that for you. Nowadays, we tend to run one program per operating system, or one logical application. I've seen that for quite a long time. Virtualizations help with that. You would tend to run an app server in one operating system, a web server in another, a database server in another. So you've got the separation of management there. Hopefully you weren't running a database server in a hypervisor, but some people do. But if you kind of think about what's going on here, you've got the hypervisor, which is providing isolation for all the guest programs and operating systems here, doing the scheduling and allowing fair allocation of resources. But then the guest operating systems are doing exactly the same thing. If you're running multiple programs in each one, maybe that's fine. But often, if you're just running one thing in there, you've got kind of two layers of this quite expensive, quite tricky processing going on. Which has led to a kind of another approach to virtualization, operating system level virtualization. And here, instead of the hypervisor, you have an operating system as you would before, but it provides means of logically separating to guest operating systems there. This gives you flexibility in upgrading because you can have your own dependencies in there. You probably can't have a completely different operating system, but you could have a different variant of the same one. So this could be a Linux kernel with Debian, Gentoo, Red Hat, and things like that. Will sometimes work. So you've got that kind of some of that freedom back. Early implementations, FreeBSD jails, Solaris containers, LXC, and of course built on top of LXC, at least in the early days, is Docker, because essentially this is what Docker is doing. These are containers. They're just guest operating systems with a load of nice wrappers around them to make them easier to manage. They're much easier to run. You've got rid of some of the dependency problems. And you're kind of doing this sharing here, so it works quite nicely. You've still got the problem that you're dependent on the same kernel, but you're in a better place. So if you kind of step back, can we do better than that in terms of our flexibility as well as maximizing utilization? So we finally come on to unikernels. So all problems in computer science can be solved by another level of indirection. As we've seen there, we're running kind of operating systems, running multiple programs on hypervisors that can run multiple operating systems. Which the famous corollary is, except for the problem of too many layers of indirection. Put another way, we're kind of doing this at the moment. So, 20 minutes in and we probably should get to actual unikernels. What is a unikernel? So, it's a specialist machine image, which you might find in virtualization. That contains everything to run a single application. So it's basically like an incredibly stripped down operating system. It's called a unikernel because it only has one process, so you can only run one thing. It still has threads, so you can run a normal threaded program, but it only has one processing, so it has none of that context switching, it has much simpler memory management, it has none of the isolation management, but it can run one thing really well. And it only generally contains the drivers that are necessary to fit one hypervisor or a small set of hardware. You can run them on natively on hardware. You no longer kind of run programs and such. You're dealing more with machine images. It's just that the machine image is essentially the same as the program with just enough wrapper code to make it work on the hypervisor. And the kind of rationale is, if you're running on a single machine, or you're running on a hypervisor, which is providing the isolation, why do it in the OS as well? Get rid of it, make it simpler, get rid of the moving parts. You might be able to see how this would work in things like if you're deploying on EC2, the hypervisor in Xen and EC2 is doing a lot of this isolation. I can just deploy my application as a unikernel. But it also scales down as well. There are a lot of unikernels run on ARM devices. So you basically get very small, efficient machine images for running on embedded devices, Internet of Things type style things. So it kind of provides a nice abstraction at this level, but it scales down nicely as well. There's a few different types of unikernels. Mirage OS is a very early and influential example, which is part of the Xen and Linux Foundation. It makes very nice, small machine images. You basically write your program. Sadly, you can only write it in OCaml. But you write it in OCaml and you compile it. And instead of an executable coming out, you get a machine image, because the compiler will basically link in what libraries you need to run on a particular target hypervisor. And given that you're trying to create these very small focused machine images, there are a lot of unikernel libraries that target particular images and runtime. So there's runtime.js for running JavaScript, Ling for Erlang, HAL LVM for Haskell, there's ones for Go, there's pretty much most languages you can think of have some kind of unikernel.
Anything for Perl?
Well, you could use the approach I'm going to take for our demo to do Perl as well. Or actually, you could use rump run. So a class of unikernels are called rump kernels, which looks a bit more like a traditional operating system. So rump run is based on NetBSD. But basically, they've gone to town on modularization. So it's a very, very modularized operating system. So you basically say, I just want this bit, and this bit. And they've also done an awful lot to move as much as possible out of that protected area in the kernel that requires the CPU privileged access and push it out into the kind of lower isolation levels. So you're minimizing what goes on then. And you can basically run anything in rump run that runs on NetBSD. I did try to get a Java application working on there, which should work, but I wasn't going to shave that yak for this demo. The one that we're going to use for the demo is a unikernel called OSV, which is a kind of general purpose guest OS that allows you to run, it supports Linux ABI format. So if you've got a Linux file with a .so output file extension, you can probably run it on here. They use quite a nice copy on write file system as well, so you can download base images and build up. And they provide base images for Java, but also for Cassandra, Memcached, Redis, and other things they think might be useful to go in there. And it's very easy to build your own as well. And we'll do a demo of this in a minute. So, pros and cons. The machine images are very small. The demo we're going to show isn't going to be that small because it needs the Java runtime, and it's got one of our old fat jars in from a long time ago, which I haven't updated. I think, Ben, you've made userauth much smaller now by taking out akka and various other things we weren't using. But some of them, so I think OSV, without kind of the runtime, adds about 10 to 20 megabytes of overhead to your application. And that's for something, that's a whole operating system, or the bits of it you need. Mirage OS, because it's even more specific, it's not a general Linux ABI supporting operating system. You're talking orders of kilobytes sometimes for the overhead for the operating system. They boot very quickly because of that reason. There isn't much to them, and we'll see some examples in booting later. They use less memory because there's less to them. They can run quickly because you don't have these context switches. You can also do some optimizations when you know that you are running within those kinds of constraints. There's things like lock-free algorithms you can use in scheduling, which waste fewer CPU cycles. There's channel-based TCP/IP, which gives you much more efficient network access. But you have to rely on the fact that you don't have to have certain locks and things in place to make those work, or at least you don't worry about the isolation. You trust the application to handle it. Then you get immutable infrastructure by default. Whilst you can bake in ways of changing the configuration, you would have to go out of your way. These are essentially appliances. You boot them up, they get their configuration from somewhere, off they go. They're more secure. It's got a very small attack surface. There's no shell. There's no libraries to hook into and play with if you kind of get root. There's no such thing as root. You can't log in. They're quite hard to attack. They're also a bit new. Okay, well, I'll do that in cons. But in theory, they are a lot more secure. You are reliant on the security of the hypervisor. They're not immune to privileged attacks, but they're very rare. Hypervisors are very mature. And I can't remember which one it was, but one of the unikernel libraries basically allow you to randomize the memory layout in the image as well. So even if you managed to get access to a box that was running it and could kind of break the isolation of the hypervisor, you just got a load of random memory addresses to kind of read from. Good luck with that. And even pretty much every unikernel style, apart from maybe OSV and rump kernels, each image is completely different when it's built. So just because you manage to root a DNS server, say Mirage OS kernel, unikernel, what you learned from that isn't going to help you with a web server one, because the kind of layout and what's included is very, very different. So cons. You are reliant on the hypervisor for multi-tenanted isolation. You can't deploy these just straight into VMware. I'm sorry, you can't kind of deploy these without that kind of isolation. VMware would give you that isolation. They're harder to debug. You can't go in and start looking at what processes are doing. You can't run netstat. You can't ping, which makes some things harder. I'd argue nowadays that's less important because our applications tend to be better at putting stuff out on external logging. Your hypervisor will often give you insight into what CPU and what memory is doing, what I/O you're performing, and you tend to get performance metrics and stuff from your application. Some of the debuggers also will bake in GDB if you want, so you can connect a debugger to it. And if you're running Java in one of the Unikernels, then you've got the Java debugger support as well, if you enable it, and that's what you want to do. It's new shiny, not batch tested. So in some ways, it's less secure on different kind of attack vectors. You'll probably manage to find a vulnerability at some point. Whether you can exploit it is another question. So a demo. Well, so originally I was going to be brave, and I was going to do a live demo. That was all set to go, and then I had a system update last week, and Docker stopped working, and I couldn't run Go linked applications anymore. I've got enough of it working, and I've videoed it. So it's not quite live, I'm afraid. I bottled out, and I was also scared that Sierra was going to kind of force upgrade any point this week, which probably would have fixed the Go app thing and made Docker better, but I wasn't going to try it. So it's an ASCII cinema. Let's play back. So, I'll full screen that. Just get the rubbish away. Thank you. I should.
It's not playing.
No. So, what is we're going to do? We're going to use OSV to build a Unikernel. And actually, I've just realised that's taken all my notes off. Okay, I'll just talk through. OSV, as I said, is the kind of one that can run general Linux shared object files. What we need to make it run is a jar file, and this is just renamed. Actually, there's a bit above there. We have a program.jar, which is just the jar that we build, fat jar we build for our user auth system. And I literally took one of the outputs from our CI server quite a long time ago to use in a demo. So it's fairly vanilla. The only things I've changed is I've baked in an empty configuration set. So it would boot because it needs some configuration. I've taken out anything that looks like a password or real URL, so when it does boot, you'll see errors because it's not really connecting to Gigi, our identity provider, because that's not something I wanted to chuck around the various demos things I'm doing. And I also made the jar executable, which is just changing the manifest file. But other than that, it is what comes out of our CI pipeline at the moment. And we need a manifest to tell the Unikernel builder what we're going to do. Now, I'm using a particular Unikernel builder at the moment called Unik, and I'll talk a bit more about that as we go, which is from EMC. And their manifest file format for building Java files is very simple. I will tell me what the program jar is, and I'll run it. So the only things we kind of have to define is we have a jar, and we say this needs to go. So you'll start to see things that look very familiar. Unik's been designed to give a Docker-like experience for Unikernels. So a lot of the APIs that they use are the same. So Unik has a manages a collection of images. The only image we have at the moment is its own instance listener. It uses instance listeners to manage the deployment onto different infrastructure. And we can see that it's running on VirtualBox, which is running on my laptop, and it's using 39 meg of memory. So that is actually a Go kernel that they have built to Unikernel that they use to manage the deployment there. So we are going to build our first Unikernel. So you give it a name, you tell it where on the file system you want to build it from. In this case, it's our user auth directory. We want to use OSV as our Unikernel builder. It supports several others, including Runtime, Mirage OS, Include OS. We want to use Java. It supports many other languages, depending on the base Unikernel provider, Unikernel image builder, and then we say which provider we want. And we're targeting this at VirtualBox. You can also target VMware, QEMU, and more interestingly, AWS and Google Cloud Platform as well. So off it goes. It's kind of doing building. It takes about a minute, and there we go. So if it's given us the details, we look at our images now. We have our new image, 133 megabytes. So this is a Unikernel running user auth which sits behind the ITV hub. 133 meg is the application, the JVM, and the operating system. What was my next idea? So we have images. We also have instances, which, if you're familiar with Docker, will be familiar here. So the current instances we have the instance listener, which is running. It has an IP address. It's on VirtualBox. So what we want to say is, well, actually, run me an instance of this image we've just built, and off it goes. Pending, we look at instances, and it's up and running. Just going to scroll off the bottom of the screen. So let's stop that instance. Damn it, I think we're losing part of the screen. Maybe not. You're right, I should have done it live. So we'll stop this, and what we'll do is we'll run it from scratch again, but we'll tell the serial output log from VirtualBox, so you can see the whole thing booting. So the OS, the VM starting, and then our application starting. And we'll know when our application has started when we see it's bound to port 8080. You'll probably see some errors because it's going to try and contact Giga in the background, and I've given it a bad URL so that it doesn't really do it. Does anyone know how long it takes user auth to start on currently, if we spin up our full OS and monitoring and everything on it?
Entire Jenkins stop and start?
No. Once you've got so if you said you auto-scaled user auth, how long would it take the next one to come up?
Maybe the instance, I think, is a lot of the time. Yeah, it's about 5 to 10 minutes or so.
Okay.
That sounds about right.
So our instance do a bit more because we have Sensu and a few other things installed, but we also have a lot of stuff we don't need. So let's try it in there. And this is just running on my laptop. So it's starting the instance, the OS is booted, it's bound to DHCP, Java started, the app started, and where is it? It's bound to port, it's ready to go. So I think that's about 10 seconds. And this isn't a particularly small it's still a microservice, but it's not a small microservice, and it's not optimized at all. But that kind of gives you an idea of, you're talking orders of magnitude in difference by taking out a lot of these things that you may not need. So, what does that mean? What comes next? So in the polemic subtitle I gave this a long time ago, it's what unikernels are and well they blow Docker out of the water, probably one day. Docker obviously saw that and then acquired unikernel systems shortly afterwards, which either means that that statement was true or false. And that's kind of interesting. I'll talk a bit about why. Unikernels aren't here. They're not used in production very much. I think there's a couple of security products that do them, and there's a few people targeting embedded systems with them, but these aren't mainstream things used, and there's not many people using them in production. But you are probably using unikernel technology, because although you may not be using a full unikernel, a lot of useful stuff comes out of this. So who uses Docker on a Mac? Most people, I'd imagine. So all the net stack for that basically came out of the Mirage OS net stack. So they've taken that kind of, the abstraction layers they needed to build to make Mirage OS work, they've then used to make Docker on a Mac work. You kind of start to see where things are going if you look at what Docker are doing with unikernels. Now, they're not doing anything directly with unikernels, but if you look at what the people who were part of unikernel systems are doing, they're contributing to projects such as LinuxKit, which probably some of the PEs might know, but is basically a minimalist toolkit for building a host OS for running containers in. So if all your operating system is doing is running containers, then you can throw away a lot of the general OS stuff you need. And that, I think some of those same engineers have been quite big in that. There's also stuff in some of the distros, some of the cutback distros, such as Alpine, where if you've kind of got Linux kits minimizing the host OS, you've got things like Alpine, which are trying to minimize the guest OS and basically look at ways of taking more stuff out of there and making it smaller. In that kind of way, it's a bit of a continuum. You're kind of still carrying on trying to make things smaller, but it's not the jump to saying we're just going to run one process. But if you look at what Docker said when they acquired unikernel systems, in the coming years, we think there will be a mix of virtual machines, containers, and unikernels for application deployment. We want Docker to be the best platform for developing and deploying on all of those. And that's a kind of important point. Docker didn't really bring much to the party in terms of virtualization. They kind of built on LXC and other things that were already there. What they did was a superb job in tooling and making it very easy to use. They've now gone on to push further, but to start with, it was the tools and the developer experience that made this work. And you can see with the Unix demo there, which does have, I think, a few of the unikernel systems people contributing to, that there are efforts to try and make unikernels simple to use in a similar way, and using some of the same APIs. I think the other thing that is interesting with Docker and containers in particular now is the orchestration. And that will be something that unikernels will need to match. One of the interesting things, and it's still in, it's not been merged in yet, is that Unix, the people that built the tool we just saw working there, have built support for Kubernetes. They provide the like libcontainer or whatever, what are they called? Kubelets. They've done one for their unikernels. So you can sort of go, well, I'm going to deploy to Kubernetes. Do I run a Docker container or do I run a unikernel? And that's still on in source. It's been there a while. They're kind of encouraging people to merge it in, but the interesting thing, it's not that big a diff. It's not a huge job to kind of basically say, run this thing that's built for a well-known hypervisor on a well-known hypervisor. It's just the kind of abstraction and the logging interface and things like that that needs to be done. So you can kind of see over the next year or so, potentially getting to the place where you can actually say, do I want to run a container? Do I want to run a unikernel? What you decide to do will depend on a few things. Unikernels will get smaller, faster. That kind of reason for doing it will get smaller. One thing that unikernels can't do is they're not portable. So you can't, it's not so easy to run a hypervisor that supports like Zen or something like that on a Mac laptop without it owning the whole machine. So you can build one image and run it in development and then in production. Whether that's important to you would depend on your workflow. That's probably not important to us, the way we generally work, because we allow our CI to build the promotable image. You could still build a machine image and run it under QEMU or VirtualBox, but that is something that you'd need to be aware of. And it would be something to play with. What's also interesting is if you wanted to move to Google, you just have to change your target environment. Not quite as easy, not quite as portable as containers, but probably nothing you'd lose sleep over. I also wanted to talk finally about a third-party demo, about a thing called Jitsi. This kind of highlights the potential of kernels, of unikernels. So Jitsi is a DNS server. Your client makes a DNS request to Jitsi. Jitsi talks to Zen and says, boot me a unikernel. And then returns the IP address to the client, and by the time the client makes a call, it has a unikernel to answer that call. Now, it's not quite as simple as that, because you can't guarantee the boot times and the speed of the latency of the network. So they've got a few different strategies for making sure that ties up. They can introduce a small delay here. They can have a listener there and not return the IP address till it's ready. They have a thing called Synjitsu, which is very cool, which basically takes the SYN packets from that TCP request and queues them until it knows that it's ready, the unikernel is ready to accept them, and then pushes them through. So you don't get the delay of like a SYN timeout and then a resend. Let's see if we can. It's not going to target the right. So there is one there. So we'll look at an example here. So this is their public example. Yeah, I knew that would happen.
Second floor Wi-Fi strikes again.
Really? Oh, you're kidding. The one thing I thought that would work. That is annoying. Oh, go on. Go on. Is he going to
Maybe this is the bit you should have recorded.
yeah. Especially I could have just I could have just screenshotted. There you go. So this is a Mirage OS unikernel, so it's particularly small, booted in 0.3 seconds. Yeah, incredibly small memory usage, and you can see the build manifest, so the kind of libraries that have been included in there. And I've not that yet. Go back. Where's the notes? Giving away what's happening. Don't show behind the curtain. And we have another one here. Sorry, you're right. This is definitely the bit I should have done. So this isn't OSV. This is a rump kernel, rump run, and there you go. That booted and served that request in the time it took to make that request. Another cool trick they use is because DNS requests have a TTL, you can basically say this unikernel is valid for half an hour or an hour, and you know at what point you can shut it down. So that's the kind of potential that you can be looking at, and how it would enable true kind of on-demand computing scaling. So if you think about serverless, there's kind of advantages to serverless, many advantages. One of the big ones is the flexibility. You can scale up and down seamlessly. But it comes at a cost. There's still an orchestration tax, because you have to kind of, as well as now you have to orchestrate applications, but with serverless, or particularly function as a service, you have to orchestrate all the functions within that application as well. So we're not there yet, and it's still quite hard to do. But actually, if you've got your application that can boot in 0.3 seconds, that's probably quite a lightweight example. But in that kind of order, then you have that kind of scalability on hand. And some of the benefits of function as a service are negated, and you're probably looking at a more generic serverless model. I think that is it. Any questions?
Yeah, with that Jitsu thing, so you sort of touched on it, I think, but could you actually then say, like, with Unikernel, I only want it to stay alive for like 10 minutes, and then after it'll just kill it?
Yeah, so you can basically configure it. I think they say they run theirs for about an hour.
Okay.
So the DNS, actually I haven't shown the DNS response. The DNS response, yeah, so the IP address is in there. It has a time to live. So basically you can say this IP address is valid for an hour, and then Jitsu knows that it can tell Zen, shut off this instance after an hour.
Right. Even if it's like still doing stuff, or?
But it just does each request. So I think you get to a point where if you might have a bit of a window in, a buffer, but if you say to a client, here's a DNS response that's valid for an hour, at that point, the next time it makes a request, it should make another DNS request after that cache after the cache has expired, to then which will then start a new instance.
Okay, fair.
I think it's funny you mentioned about user auth specifically, because there is a problem with that service in that it takes longer to boot up than is the traffic spike of ITV speed time.
Yeah.
And so auto-scaling doesn't help at all with quite a lot of problems we have online, because at 9 PM, all of the traffic happens in 2 minutes.
It's the same for most of our systems in online, because
So if we had this sort of system, it would be quite a game changer for us. There would be a lot of problems we would no longer have to worry about.
Yeah.
What do you think has to happen for it to be clutch-ready?
It's a tricky one, especially given as I'm leaving. So I think nothing. I think you could run this in production. I think if we move to a Kubernetes kind of support where for containers that would also accept unikernels as well, you could start running mixed states. So you can start running things in production with a bit of a safety net. That would be a way of doing it. You could probably do that now, but it would be a lot of orchestration, because you could just say, well, user auth consists of this image and this image. One is our current one is the one we bake there, and we'll put several of them behind a load balancer. So if the unikernel one wasn't working out for some reason, you still got that. So you could do it now, but I think it'd be a lot of effort. It might be worth it actually, given that, and I think it'd be fun. But I would guess once you've got kind of that orchestration layer in place, that makes it easy to do. That also, that almost becomes just a config file.
Is that kind of tooling from people like Docker would help us out a lot to make it an easy transition if you want to make it?
Oh, Kubernetes is Google. I don't know who actually owns. I think it's a foundation. Isn't it? But yeah. So if we went that way but I'm guessing other orchestration engines will get that support at some point.
We should get a lot of the benefits in terms of boot time when we switch to containers next year. Because they come up in a few seconds. So, but then you don't kind of get the smaller attack surface and stuff like that, which is nice.
It's not really a question, but it's just quite nice how the very first computer you showed was just a process loading hardware. It's basically kind of come full circle. That's the closest thing you can.
Yes. I kind of didn't know whether that history was kind of going off at a tangent or not, but actually, the point is that we think about computers as having to run lots of things, but they don't. We do that because for financial reasons, historical. And given the tools we have now, there are other ways of doing that. You can start looking at other, you don't necessarily need multi-programming or multi-processing. I meant to call that out explicitly. Thank you.
Any more questions? Thank you, Lee. I'd actually kind of a farewell talk actually, because Lee, you're leaving in November now.
Yep.
Yep, heading off to Sainsbury's, the enemy's down the road. Like I said, this is kind of the first tech forum we've had. Actually, a lot of new faces in the audience, so nice to see you. Well, normally we run these every month, and the idea is that the internal people, if you want to talk, can come here and have a go. Kind of a nice friendly crowd, and also external people as well. So we should have Amazon coming in. Got people from GDS, the Government Digital Service, in the line as well, and some AI researchers from UCL coming in. But if you know any friends in the industry or anything you'd like to invite in, please pass on my details. I'm Tom Clark, by the way. And I think there's some cakes left at the back if you fancy those. And then this will be put up on YouTube later on, and I'll send around the links. Final thing is, this is obviously the Tech Forum, but this evening is the Tech Social. Again, runs the last Friday of every month. That's going to be over at the Eastern from about kind of 6 o'clock onwards. We're also celebrating or commiserating Akin and Mittal from online, who are technically leaving, but they're moving down to the 3rd floor, but basically they're going to be dead to online anyway. So thank you all very much. Cheers.